There we go. All right. Ooh, not a bad turnout for the day before spring break. Turn up on the floor. All right. Good morning, everybody. No quiz today. Hopefully you guys remembered, or maybe you didn't remember and you studied anyway. So, hey, that would be pretty good though. Let's go ahead and pick up where we left off. So, I'm stalling while I find my page. Give me a second. There we go. Okay. All right, so we left off, we finished the section on hydride reductions the other day. So now we're going to start talking about organometallics. So you may wonder, what is an organometallic? Well, the name really is pretty self-descriptive there, right? An organometallic has an organic portion, right? So we can have an R group, just a carbon chain of some sort, that's bonded to a metal. And we'll just represent metal with MT for right now. Because there's a couple of different metals that are commonly used. All right? And organometallics, they can be used, they're very versatile. I could teach a whole class in organometallics. They can be used for lots of different things. We're going to look at some of the more common ones that are used in organic chemistry. And we're going to see what they do. Right? There's going to be three primary types of organometallics that we're going to look at. All right? First one is called an organolithium. As you probably guessed, this one has a lithium in it. Funny thing about organometallics is that for the most part, they're not very stable. You can make them, but usually whenever they're made, they have to be used immediately. So they're not something typically that you can just like open, up a chemical supply company's catalog and just order. There are a couple of them that you can do this with, but even then, they're very, very sensitive. They have to be stored under very, very special conditions. So usually we just make them and then use them. And organolithiums are included in them, right? Organolithium generally is going to look like that. All right, so it's going to be necessary to learn how to make it. Right? Here's how you generally make an organolithium. You start off with an alkyl halide. And you add 2 equivalents of lithium metal. That'll give you your organolithium plus a waste product, lithium halide, whether that's lithium chloride, lithium bromide, just depends on the type of alkyl halide. And one nice thing about this, though, you can design these syntheses to give you whatever R groups that you want, right? So if you want a methyl group, you would use something like a methyl bromide. Okay. You might still want something bigger. You might want, I don't know, you might want a cyclohexane ring, right? Cool, we can do that. Just use cyclohexyl bromide. Same process. Gives you the organolithium that you want. Easy peasy. Huh. It's easy peasy on the board. In practice, it's a little harder. Like I said, these things are pretty sensitive, so even when you make them and use them immediately, you still have to follow a bunch of precautions. I'll talk about that in just a minute after I tell you about the synthesis of all of them. All right, so that's one. That's organolithiums. Number 2, you have something called the Grignard reagent. Grignard has a silent G. It's French. Grignard reagent. All right. To make a Grignard reagent, first of all, let me show you what it looks like. A Grignard reagent looks like this. It's got your R group attached to a magnesium, which is then attached to, again, a halide. Okay. And how you make this is that you start off with your alkyl halide. You add in some magnesium metal. And you have to have a very particular solvent for this. And that's diethyl ether. Okay. The reason you have to have diethyl ether is because Grignard reagent is very, very fragile. It's very, very sensitive, not very stable. So basically what happens is your Grignard reagent is, once it's synthesized, gets sort of surrounded on both sides by diethyl ether. And I don't really know a specific line. I'm going to use little wavy lines here. Little wavy lines. Very technical this morning. Basically, those oxygens in the diethyl ethers help to sort of stabilize the magnesium and leave everything in place. Like a lot of organometallics, Grignard reagent is very, very sensitive to atmospheric contaminants, like water, right? You expose a Grignard reagent to air, it's going to decompose. You expose it to acetone, it's going to decompose. You expose it to methanol, it's going to decompose, right? So if you're ever doing a Grignard reaction, like in the lab or something, you have to be very, very strict about the glassware that you use. It has to be perfectly clean, perfectly dry, or else being contaminated. I used to do this lab. in the OChem lab rotations. I don't do it anymore because it is really hard to do. And the yields, we would get like 0.5% yield on these because students just could not keep the conditions tightly controlled. So the solvent is very, very important. Not all organometallics are quite that sensitive, but it's fairly representative. All right. The last one's called an organocuprate. All right, and this one's going to involve copper. An organocuprate looks like this. It's got a copper, and the copper actually has 2 R groups attached to it. And the copper is actually the anionic portion of a salt. It's actually part of a salt. So copper's got a negative charge here. One of the few times you'll see copper with a negative charge. Because it's in a salt with lithium. That's what an organocuprate looks like. To make an organocuprate, first you have to have organolithium, right? So it's a little bit extra tricky because first you have to synthesize the organolithium and then you have to synthesize the organocuprate, right? But basically what you would do, take your organolithium, add in some copper iodide, and both of those R groups, one from each molecule, is going to attach itself to the copper. Like that. And you'll also get some lithium iodide as a byproduct. By the way, organocuprates and Grignards are just like organolithiums in that you can tailor the R group to be whatever you want. Methyl, ethyl, isopropyl, tert-butyl, whatever. Okay. One other note about these. Y'all remember when we were talking about hydride reductions, we said that we can have strong hydride reducers, like lithium aluminum hydride, something like that. And then we can have mild ones, like dibial H. Same thing here. We can have strong organometallics and we can have mild ones. All right. Organolithiums and Grignards. Those are strong organometallics. Very, very strong sources of R minus. I'll talk about that in a second. Very sensitive. Organocuprates, on the other hand, they're not quite as strong. These are mild sources of R minus. And just like with the hydride reductions, that plays a part in what type of product that you're going to get from a given situation. Okay. Any questions so far? Okay. So you're seeing some commonalities here with the hydride reducing agents. You can have strong, we can have mild. Also, just like hydride, these guys are strong bases. And strong nucleophiles. Why are they strong bases and strong nucleophiles? Because all of these serve as sources of R minus. Hydride sources serve as sources of H minus. Organometallics are going to give us R minus. That means you're going to have a negative carbon in each one of these groups, a carbanion. Negative carbons are extremely strong bases. And in turn, unless they're sterically hindered, strong nucleophiles as well. Does that make sense? All right. All right, that's kind of the introductory stuff. You know what organometallics are, how to make them and stuff. Now, let's see them in action. All right, it's going to be very similar to what we did last time, right? We're going to have basic categories of reactions. Let's see what they do with aldehydes. All right, so let's just take an aldehyde. We'll take acetaldehyde. Let's just add a Grignard reagent here. Just like with hydride reductions, basically this is a two-step process, right? You have the organometallic in the first step, and then you follow it up with a proton source. Usually water, although it can be an alcohol as well. Excuse me. All right. You tell me what's going to happen here. Based off of prior knowledge, what do you think is going to happen? Dude, somebody lowered the chair. That sucks. No, that doesn't feel right. I like sitting up tall so I can, pretend I'm more important. What's going to happen here? And by the way, for those of you who continue to insist that I'm going to try to trick you, this is not a trick question. So what's the purpose of Grignard? What's it going to give off? What's it a source of?
Magnesium.
What's that?
Magnesium.
It's not going to be magnesium. Remember, all organometallics, they serve as what? Sources of what? R minus, right? So what's the R group in this case? CH3, yeah. R group is always going to be the carbon chain, right? So this is going to give off CH3 minus. What is that CH3 minus going to do you think? Good thought, but actually an aldehyde hydrogen is not very acidic. So something else is going to happen. Yeah, exactly, right? We got full negative over here. We got a strong partial positive over here. That's going to attack just like the H minus did. Literally, it's like you're just replacing H with, in this case, CH3. Right? Well, what type of reaction do you think this is going to end up being? A nucleophilic addition or nucleophilic substitution? It's going to be an addition, right? Because it's an aldehyde. Because it's an addition, that means a pair of electrons is going to hop up to oxygen. Now you have that extra methyl group attached. Last thing that happens is what? Protonation of the O. Very good. Voila. You have a secondary alcohol. And that's what aldehydes tend to give you. Aldehydes, if you react them with an organometallic, give you a secondary alcohol. With one exception. We'll get to that in a second. Any questions on how we got that? You're going to see, again, a lot of familiarity from the hydride reactions. Every aldehyde will give you a secondary alcohol except for one. It is possible to make a primary alcohol with an aldehyde. How on earth would that happen? I'll give you a chance to guess it. What type of aldehyde? What would my aldehyde look like that I would have to use to get a primary alcohol? Oh, you're gonna kick yourself. Well, if I want a primary alcohol, what does that mean about the number of R groups here? How many R groups we got on this carbon? 2. 2 gives secondary. How many gives primary? 1. So basically, we want to get rid of one of these, right? One has to come from the organometallic. So that means this little fella is the only aldehyde that can give you a primary alcohol. Yeah, so if you did the same reaction here, you'd get a primary alcohol. Anybody recognize that aldehyde? Very special aldehyde. What's it called? One name for it is methanol, but you probably know it as, what's your cue? Formaldehyde. Yeah, everybody's favorite aldehyde. Okay. That's actually not my favorite aldehyde. My favorite aldehyde is benzaldehyde. You know why? It smells like cherries. Yeah. So generally speaking, if you use an aldehyde and you react it with a strong organometallic, you're going to get secondary alcohol. However, there is that one exception, and that's formaldehyde. Formaldehyde will always give you a primary alcohol. Okay? Does that make sense? Any questions? Well, here's a question for you. How about a tertiary alcohol? You think there's any way we can get a tertiary alcohol? How can we get a tertiary through this method? We want a tertiary. What does that mean about the number of R groups that we need in the end? What's that? You need 3, right? So you know you're going to add 1 through the organometallic. That means you need to start off with 2. That means we're going to need a ketone. All right, so let's see what happens with ketones. We have a ketone. Let's say we have that. Oh, we'll use an organolithium just for fun here. Let's see. All right, mechanism exactly the same. No differences. Your R minus comes off. In this case, it's going to be a negative ethyl group. That negative ethyl group attacks your carbonyl carbon, drives electrons to oxygen. Now you can see we have that extra R group attached. And then we can protonate it. and we have tertiary alcohol. Okay. And that stands to reason. Extra R group at the beginning means an extra R group at the end. Any questions? Now, I haven't shown any like this yet, but this is a situation you can run into for either the aldehyde or the ketone. So this applies to both of them. I'll just use a ketone. We'll use this one. Use a Grignard reagent this time. All right. The only thing I did there, number one, I used a different organometallic, but also I changed these two R groups. I made them non-identical here on your original ketone. Process is going to work exactly the same, right? Lather, rinse, repeat. As far as the mechanism goes. And as expected, we started off with a ketone. We got a tertiary alcohol. That's good. What's the only difference between this one and the previous one? Good old stereogenic center. So that is something you have to watch out for. We do sometimes in the process of either with a ketone or an aldehyde, make a new stereogenic center. Right? We follow the same guidelines. This sp2 carbon is trigonal planar, flat as a sheet of paper. So we're going to get a racemic mix out of this. Okay, does that make sense? Any questions so far? All right. Now, what I've shown you with both aldehydes and ketones, that only applies to organolithiums and Grignards. It only applies to the strong organometallics. We can set up a reaction with an organocuprate. Let's use acetone here as an example. Let's see, put a couple of ethyl groups over there. Okay. What do we say the difference was between an organocuprate and then the Grignard organolithiums? What's different about organocuprates? So you have to do that for all of them. It is a mild organometallic. Any just instinctual guesses as to what the results will be here? What's that, Josh? No, what was the sign? Josh gives me the throat slash here. Although not quite as dramatic. It wasn't with the thumb. It's like, no reaction. Yeah. Aldehydes and ketones are not reactive enough to react with organocuprates. So that's kind of nice, right? That means there's fewer reactions you have to keep track of. All right. Very good. That's it for aldehydes and ketones at the moment. Now, just like last time with hydride, we're going to look at carboxylic acid derivatives. All right. And again, you're going to see some familiarity. This first category is going to include acid chlorides and esters. So in these cases, they do the exact same thing. The only difference is what type of leaving group you're going to have. All right. So I'll show you with an acid chloride. So let's say we have that, and let's see, we'll use an organolithium. And set it up just like we have in the past. All right. What type of reaction are we going to have here? Nucleophilic addition or nucleophilic substitution? Yeah, substitution. So armed with that knowledge, tell me what the first step of the mechanism is. Yep, exactly right. The ethyl from your organolithium attacks your carbonyl carbon, which has a strong partial positive. But in this case, since we have a good leaving group, Cl is just going to leave. And what type of compound did we make? What is that? That is a ketone. Right. Now, funny thing about ketones and organolithiums, we just learned they react with each other, right? So, guess what? The standard procedure here, even if it's not always noted, is that you use two equivalents of your organometallic. Yep, so you can get another negative ethyl group that comes in, and it reacts with the ketone. It does so exactly in the same manner that we just went over. And you end up with tertiary alcohol. You always end up with a tertiary alcohol here. Also, it doesn't matter if you have an ester or an acid chloride. The only difference, if this was an ester, your leaving group would have been OR minus instead of Cl minus. It works the same way. Okay. You know what's nice about these? You never have to worry about making a new stereogenic center because the same carbon always gets two identical R groups added to it. So there's something that's kind of nice. Okay. That makes sense? Any questions so far? All right. I'm going to adjust the title of this just a little bit now. We're just going to focus on acid chlorides for this next part. Let's try an organocuprate. All right, so we've already talked about the fact that organocuprates are mild, right? They're mild organometallics. So they can't react with everything. However, acid chlorides are super reactive species. I already told you about, if I just opened a bottle, it would make some smoke. That was HCl gas. Funny story, at least it is in retrospect. When I was in graduate school, I used to work a lot with peroxides, and I was trying to do a process called microencapsulation of peroxides. I was basically trying to trap little droplets of peroxide in these little shells, almost like an M&M, right? And I was exploring different ways of making these shells, and one of them was to make something called a polyester. Make a polyester and use an acid chloride. So I took an already unstable material, peroxide, and mixed another unstable material with it, an acid chloride, as part of my formulation. Guess what happened? Nothing. It just dissolved, and they just dissolved in each other. Cool. Stuck it in the fume hood while I turned around to go get something else. I turned back around, and the fume hood is filled with thick orange smoke. Why it was orange, I don't know, but it was. It was something. You ever seen those pictures, like those NASA pictures of close-up pictures of Jupiter and like the Great Red Spot and all that stuff? That's what it looked like. It was pretty cool, actually, except that it wasn't. So, because I had to clean it up. It left this like orange sticky residue all over the fume. I had to scrub it out with sponges. But it goes to show you, acid chlorides are very, very reactive. That's my long-winded point here. So they're definitely reactive enough to work with an organocuprate. Right? Well, if we can react an acid chloride with an organocuprate, how's it going to do so? Same way as it did before, right? Organocuprate serves as a source of R minus. It's got two of them, so let's just take one of them, doesn't matter which one. It's going to attack here. Cl minus leaves. What does that give us? Ketone. Very ugly drawn ketone. I'm ashamed of that, but now what? It's done. Very good. That's it. We learned that ketones are not reactive enough to react with organocuprates. So if you want to convert an acid chloride to a ketone, that's how you do it. If you want to convert an acid chloride to a tertiary alcohol, then you would want to use a strong organometallic. Okay, that makes sense? Take a quick look at esters, right? Just to recap what I previously showed you. You can take an ester and react it with either an organolithium or a Grignard reagent. And just like with acid chlorides, you always get tertiary alcohols. I'm not going to go through the whole mechanism. It's the same as the one we did before. The only difference is your leaving group is OCH3 bonds. All right. Well, what about its behavior with organocuprates? Well, if you think back, there's certain cases where we've been able to lump acid chlorides and esters together because they do the same things. However, strictly speaking, if you remember back to our reactivity scale, how do acid chlorides and esters compare in reactivity? Are they about the same? Is one more reactive than the other one? What? Yeah, look back if you have to. How do acid chlorides and esters compared to each other as far as general reactivity.
Acid chlorides are more reactive.
Acid chlorides are more reactive. Yeah. They're close enough in a lot of cases to do the same thing, but acid chlorides definitely are more reactive. Because of that, we see you have this situation in R. Esters are not reactive enough to react with organocuprides. Right? So of all four things we've seen so far, aldehydes, ketones, acid chlorides, and esters, the only one that can react with organocuprides is acid chlorides. Okay. Are there any questions so far? All right. Okay. Trying to find my page. Give me a second. Okay. That's actually all the acid derivatives that we're going to talk about. We don't see organometallics typically used in this manner with carboxylic acids or amides. So we're not going to worry about it. There are a couple of other species that can react with organometallics. First one is everybody's favorite, oxides. And again, honestly, really, if you think about it, this isn't anything new. We've talked about this already, right? We know that if we have an epoxide, and we have a strong nucleophile present, what's going to happen? The nucleophile, yeah, the nucleophile attacks one of the carbons in the ring, breaks it open. This is just that reaction. The only difference is this is the first time you've seen an R- group used as one of these nucleophiles, right? So it works the same exact way. So we had a Grignard reagent here. Right? So yeah, it works exactly like previous epoxide reactions. CH3 minus attacks one of the carbons, breaks open the ring. The oxygen protonates. And you make an alcohol. You can make primary, secondary, or tertiary alcohols with this, just depending on what else you have bonded to your epoxide ring. I'm stalling to let you guys finish writing before I do my next example. Can I erase yet? Can I not erase? Going once, twice. Okay. Just a quick reminder on epoxides, just in case you forgot. Please don't get a pre-break this time, just for differences. One nice thing about this is that epoxides are so reactive. Epoxides work equally well with all three of these. So you can use any one that you want. So we're going to have R-, in this case ethyl, attack. Which carbon do we attack this time? Least substituted. You can tell because the oxygen is neutral, right? So just wanted to give you a quick reminder on that. So in that case, you have an ethyl group hanging off of the same carbon as the oxygen. Whoa, I just screwed up. Never mind. Just ignore what I just said. I have the oxygen on the wrong carbon. Because this went this way. So in this case, we ended up with a tertiary alcohol. Like I said, you can get any of them, just depending on what the situation is.
So there one too many carbons on the middle one?
This one?
The bottom left.
Ooh, yes, there is. Thank you. There we go. Good job. Good catch. So yeah, for these, basically just apply all the same knowledge that you already did about oxides. You just have a new nucleophile to work with. That's it. Works equally well with any three of these. Okay. Any questions? All right, this is going to work out well. We got just one more reaction to show. And that brings us to a good stopping point. So, nice. One other very specific reaction you can do is Grignard reagents. And it has to be Grignard. Organolithium will not work this way. Grignard plus carbon dioxide. Right? So in this case, carbon dioxide, if you don't know the Lewis structure, looks like this. And if you think about it, it really is. Carbon dioxide is a carbonyl compound. It's almost like an uber carbonyl compound because it's got two carbonyls. Sort of. Two carbonyls with a shared carbon. All right. We can put in a Grignard. We'll just do this one. And you have to have a proton source. However, in this case, water and alcohols are not acidic enough. So you actually have to put in something acidic, an actual acid. We're just going to use hydronium ion there to represent that, H3O plus. As for the mechanism, it's exactly what you think it would be. You got your R minus. You have a really strong partial positive right here. That attacks. Pi electrons are going to move up on one of the oxygens. So this is going to be a nucleophilic addition. So you create that. And that gets protonated by the acid that you make. And what type of product have we produced as a result of this? C double bond O with an OH. What's that called? That is a carboxylic acid. Oh, we went went through a lot of them today. But as you can see, again, there's a lot of common patterns. So you can sense a lot of patterns. All right, that is a great stopping point. We're not done with the chapter yet, but the other sections in here are very distinctive and kind of separate from this. So, are there any questions? All righty. Some of you I'll see in lab this afternoon. For the rest of you, have a great Easter break. Yeah. Just doing NMR again today.